All right, so we're going to do a couple more of these stoichiometry examples. We're going to talk about limiting reactant, and we're going to talk about theoretical yield. And I'm going to see if I can get a couple of titration questions in too. And after that, we'll be done. So we have another example here of stoichiometry. And all of the other topics are related to stoichiometry, right? Everything we talk about with theoretical yield, actual yield, percent yield, all of that is related to stoichiometry. So let's say we have a reaction like this. Balance it. I want you to balance it. All right, let's say we have a reaction like this. And the question is, what mass of CO is required to react with 25.13 grams of iron oxide, iron 3 oxide? Right, so notice it's asking you, it's not asking for moles, now it's asking you for mass. And that's important. But the thing that we know about these stoichiometry problems is everything starts with moles, right? So if we got moles, we can figure out mass, no problem. But first we got to balance this equation. All right, how would you balance it? So let's go ahead and take inventory. We got Fe, oxygen, carbon. Fe, oxygen, carbon. Oh, we got 4 oxygens, 1 carbon, 2 irons, 1 iron, 2 oxygens, and 1 carbon. What do we need to do?
Multiply oxygen and iron by 2.
All right, so you want to put a coefficient of 2 in front of iron. I agree with that. And you also want to put a coefficient of 2 here.
Mm-hmm.
All right, let's see what we get from that. So this is times 2, that's 2. This is going to be also be times 2, so that's 4. This is times 2, and that's going to be 2. Right, so now what do we need to do? Because it looks like the oxygen is going to give us a problem. Because when we balance the oxygen on the other side, we're gonna have more. So let's do that. So what do you want to put? What do we put in front of CO? What do we need to do there? We want to put a 2 here. Let's see what that'll give us. So this is going to be actually 2 plus 3, which is 5 if we did that. And this is going to be times 2. So now that's 2. Got a problem, don't we? That's balanced. This isn't. And we don't want to touch the iron because it's already good. So we need to probably do a different coefficient than 2. The 2 in front of the iron is fine because that's by itself, so that's no problem. But we want to change this coefficient. Instead of doing 2, that race is so big. Let's try something else. Let's try 3. All right, because if we put a 3 here, let's do that. So we'll erase all of this except iron. If we put a 3 there, that's going to give me 6 oxygens. It's going to be 3 times 2. And then it's going to give me 1 times 3 carbons, which is 3 carbons. 3 carbons. All right, so that's that. And then we go over here now, and let's balance the carbons by adding a coefficient of 3 here. So that's going to give me so oxygen is now going to be 3 plus 3, which would be 6, and then carbon, which is 1, would be 1 times 3, which is 3. So now everything is happy. Did not try to do that. I don't know why iPad did that. That's such a stupid feature. Trying to be like Samsung. All right, everything is balanced now. All right, so now let's answer this question. If I start out with 25.13 grams of iron oxide, can I do anything with that number as it is right now? When I'm doing stoichiometry problems and I'm using these stoichiometric ratios to go from one substance to another, am I ever working in grams?
Would you work in moles?
Always work in moles. We always work in moles for these problems. So no matter what unit you're given, you got to find a way to convert that unit into moles, right? So for grams, it's easy. It's just grams over molar mass will give me moles. What do I need? I need the molar mass of iron 3 oxide. Can somebody look that up real quick? Always work in moles for stoichiometry problems. Never grams or liters or atoms or whatever. It's always in moles. That's the only way you can convert from one substance to another in a stoichiometry problem like this, is by converting everything into moles and working in moles. All right. Anybody got it yet? I think it's 159. 159.69 grams per mole. So we're going to calculate moles from that. So let me put that here. Calculate, we can go from grams to moles. So it's going to be 25.13 grams divided by 159.69 grams per mole. All right. And that's going to give me 0.157 moles. All right. Everybody okay with that? That's the strategy. If my starting unit is in anything but moles, my first step is to convert everything into moles. That's my currency for stoichiometry problems, is moles. I don't work with any other currency. I ain't working with dollars or rubles or pesos, right? It's got to be moles. So now the second step, well, the first step is actually balancing, which we did already. Second step is use the stoichiometric coefficient. From the balanced equation. Right. So what is the relationship between iron 3 oxide and CO? Because that's what they're asking. What mass of CO is required to to react with 25 grams of iron 3 oxide. What are we looking at? What relationship? What do we want and what do we want to get rid of?
You said of which two?
Say again. I'm asking what the relationship, which relationship are we going to use from the equation up top? If it's asking us about CO and iron 3 oxide, which relationship are we going to use?
The 1 to 3.
1 to 3. All right. So now we know that. What do we want? We want CO and want to get rid of iron 3 oxide. So we're going to say that this is 0.157 moles of Fe2O3 times 3 moles of CO over 1 mole Fe2O3. That we get that 3 to 1 straight from the equation. That's why we have to balance it first. All right. So now that's and that's going to give me moles of CO, but it didn't ask for moles, but that's what we're going to find first. Now that'll give me what do you have? And did I put the right? Oh, I messed up. Hold up. Let me go back. Anybody got it yet? Is it 0.472?
Yes.
Moles of CO. All right, good. So now finally, if it asks us for grams, because it asks mass, we need to do that. We need to take the moles of CO and convert it back into grams. So CO has a molecular weight of 28 grams per mole. So from moles to grams, it is moles times molar mass, which is in grams per mole. All right, so the moles are going to cancel. So we need 0.472 moles times 28 grams per mole. Let me write that. 28 grams per mole. That's the molar mass of carbon monoxide. All right, so that's that times 28. All right, and you should get 13.2 grams. Is that right? Yes, no?
Yeah, it look right.
I will take it. It looked right. All right. So whenever, I think we need to recap these stoichiometry problems. Whenever we're working with them, everything needs to be in moles, right? So because your stoichiometric ratios up here, let me make this a little bigger. Your ratios up here, when we talk about relative amounts, we're dealing with moles, right? We're not dealing with grams or milliliters or liters or whatever. It's always in moles. So anytime you want to convert from one species to another, the currency is moles. All right, let's do one more. Yeah, let's do one more stoichiometry problem. Then we're going to move on to limiting reactant and theoretical and percent yield. So let's do this. Let's take gallium and react it with O2 to give us gallium oxide. All right. First thing, balance. That's the first thing we got to do. And then while you're balancing that, somebody's giving me those numbers, I'm gonna write the question. I'm gonna actually steal this question up here because it's the same type of question. I don't have to rewrite the whole thing. So the question is, what mass of gallium oxide is produced from 29 grams of gallium metal? And this is the equation. First thing we're gonna have to do is balance this thing. And once we balance it, then we can go into our strategy of converting one thing into the other using stoichiometric ratio. All right. How do we balance this? Hold on, let me zoom out so you can actually see it. And I'll fix the question later, but we're looking for the mass of gallium 2 or gallium oxide from gallium metal. Is that balanced as is?
No,
All right,
it should be 2, 3, 2 as the coefficients.
all right, let's see that. 2, you said 2, 3, and 2. All right. Got a problem because now gallium on the other side is gallium. So we got 4 gallium, 6 oxygen.
Oh, so
like
4, 3.
Okay, so I like the 3 in front of oxygen, but this has to be 4. So 4, 3, and 2. Good. All right. So now we balanced it. Now we need to convert gallium metal into gallium oxide. And so we're going to exploit this relationship. We want to find out what this and this, what the relationship is between those two. And the coefficients matter, so we'll keep those in there. All right. So we want gallium oxide. We have gallium metal. So what we want, we put it in the top of the ratio. So that's going to be here, 2 Ga2O3 over 4 Ga. That's our relationship. And this is going to be times whatever number of moles of gallium. So now we need to convert gallium, what we have, gallium metal, into moles. How do we do that?
Multiply that number by the molar mass.
Or divide it, right? Because it's grams, you got grams and it's going to be grams over molar mass. So what's the molar mass of gallium metal? It's just the atomic number, isn't it? So whatever the atomic number is for gallium, that's the number that we're going to use to find the number of moles. So I think it's 69.72. So for gallium, it'll be 29 grams divided by 69.72 grams per mole. Right, so grams are going to cancel. We're left with moles, and let me just put it in down here. Right, so that's going to be 0.416. Moles of gallium. Same strategy. Started out with grams, you had to convert it into moles, and then you take the relationship that you want to exploit from the balanced equation, and which is two moles of gallium oxide over 4 moles of gallium metal. So the moles of gallium are going to cancel. Let me make sure I indicate that over here too. It's 2 moles, 4 moles. Because all of our stoichiometric relationships are going to be mole to mole ratios, right? That's what that's just what we use. So that's going to be 0.832 divided by 4. Right? And then that'll give us a total amount of, let me shrink this, 0.208 moles of gallium. Not gallium, it's the gallium oxide, sorry. Right, but it asked us for grams, if I'm not mistaken, said what mass. And I'll clean this up before I post it. What mass of gallium oxide is produced from 29 grams of gallium metal. So we need to find out what so we have moles of gallium oxide. How do we get that to grams again?
Using the molar mass.
The molar mass. So this is going to be moles times molar mass equals grams. So it's going to be 0.208 moles times the molar mass of gallium oxide, which is, somebody can Google that right quick. What's the molar mass of gallium oxide? I don't know it right off top. We can figure it out though. I think gallium, we said, was 69, and then you got 2 of those, so that's going to be 138, and then 3 oxygens, which would be 48, 138, and 48. What is that? 186. Is that right? Yeah, it's 187.44. All right, so that's going to give us 38.98, or actually 38.99 grams. Which is important, right? Because this is a great segue into the next part of this discussion, which is dealing with limiting reactant and theoretical yield, and how much of one reactant will, how much product one reactant will give you compared to the other, right? So we're going to talk now about the limiting reactant, right? And the limiting reactant is, by definition, is the reactant, we can think about it two ways. It's the reactant that gets used up first in a reaction. Let's say it that way. Right, it's the reaction that gets consumed first. So all of it is gone. And the reason it's called limiting is because once all of that reactant is gone, the reaction is over. Let me give you an example. If you take A plus B, going to some compound C, right? And let's say A is limiting. Once you use up all of A, then no more C is going to be formed. So if A is limiting, when it's all gone, the reaction stopped. Right? So if A is limiting and during this reaction and all of it gets used up, then the reaction stops when the limiting reactant runs out. And let me give you an example. If I'm baking cookies and every batch of cookies takes 2 cups of flour, and 100 chocolate chips. And that gives me, let's say, a batch of 30 cookies. Right? And let's say that the flour is limiting. When I run out of flour, I can't make any more cookies, right? So if I only got 1 cup of flour, and then 100 chocolate chips, no nookies. Sorry. I meant to say no cookies. Right? I get no cookies because the recipe calls for 2 cups of flour. So when I run out of flour, I'm effectively unable to make cookies. All right. So that's how the limiting reactant works. Once that reactant is used up, then it's over. Like the reaction is done. It will not go any further. We're actually going to do the limiting reactant lab soon, like in the next week or so. We're not going to have lab tomorrow. I need a catch-up day so I can catch up on a bunch of stuff. But normally we'll do it next week, because I think the Tuesday people are ahead of the Wednesday people by 1 lab. So we'll do the limiting reactant lab, and it's a very, very nice lab. It's like potassium oxalate and calcium chloride, and one of those is limiting, but the way you find out is there's a little test you have to do at the end to see if you get more precipitate or not, because the calcium oxalate is going to precipitate out of solution. So we'll find that out though. But when you think about limiting reactant, that's basically what it is. It's just saying that in a given reaction, you'll have a specific amount of each reactant, and one of those is going to be limited, because one of those is going to give you a specific amount of product, where the other one will only give you a certain amount of product as well. So another way to think about limiting reactant is the reactant that's going to give you the least amount of product. All right, so let's just do an example. Let's do an example and bring this all together. All right. So let's say we have a reaction, silicon plus N2 going to silicon or Si3N4. All right. So now the question is this balanced? Everything comes down to balancing. If it's not balanced properly, your coefficients are going to be off. If your coefficients are off, you're not going to calculate the limiting reactant properly. So we're going to do this, and we're going to ask the question, which is limiting when we use 2 grams of silicon and 1.5 grams of N2. All right. And so once we figure this out, we're going to see which one gives us the least amount of product. That's the thing that we're trying to do. We're going to figure out which one gives us the least amount of product. And it's not always readily apparent, because I know you see 2 grams and 1.5 grams, and you immediately probably start thinking, well, you got less nitrogen than silicon. So that means that that's going to get used up first. But that's on we're looking at, we got to look at it on the molar, the micro level. The grams that we're weighing out in the lab is not the same. That's not going to tell us anything. We got to look at it on the micro level. So again, let's balance this first. And this is transactional only if everything is in moles. So let's balance the equation. What would you do to balance that?
Use 3 and 2 as the coefficients.
Okay, good. So 3 here, 2 here, that's balanced. All right. So now we want to find out how many moles of each we're working with, right? So we got 2 grams of silicon, 1.5 grams of N2, that 2 matters, right? So for silicon, the molecular weight of that, or the atomic mass of that, is 28.09. So we're going to take those grams, convert them into moles. We're going to convert them both into moles. So 2 grams of silicon divided by 28.09 grams per mole. That's the atomic mass of silicon, which we can use as we can call it the molar mass. They're interchangeable. That's going to be 0.0712 moles. All right. So we're starting out with 0.0712 moles. And we're also starting out with 1.5 grams of nitrogen. And because there are 2 nitrogens, that mass is also going to be 28 grams per mole, because nitrogen has a mass of 14. So 28.02 grams per mole. And that's going to give me 0.0535. Let me say, yeah, moles. So this is Si, this is N2. So now we can work, because everything is in moles. So we can start converting product, find out how much product we're going to get. So let's find out how much product we get. How much product we get when we start with the silicon. Let's start with silicon. All right, let's start with silicon. So we look at the balanced equation. What is the relationship between silicon and the product? It's right here. This coefficient is 3. Over here is understood to be 1. All right, so let's find out. That's the question you're asking when you're talking about limiting reagent. How much product are you going to get with either one of those 2 reactants? So how much product from silicon? So we know we got moles right here, right? So silicon moles is 0.0712. We'll put that over here. And the relationship between silicon and the product is 3 to 1. So we're going to put this here, 1 mole of Si, what is it, Si3N4 over 3 moles silicon. That's the relationship. It's a 3-to-1 ratio. So 0.0712 divided by 3. We got 0.0 0.0237. Everybody following that? So this is what we're doing now. We balance, then we convert everything into moles. And now we're going to find out from the stoichiometric ratio how much product we get from silicon. Because it doesn't matter if we know the amount of product or not. If we have a ratio, that's our conversion factor. We can convert anything from one to another as long as we got a conversion factor. Right? So that stoichiometric ratio is my conversion factor. So now we're going to ask the same question about nitrogen. How much product do we get from nitrogen? So this is N. We're going to make that N2 instead of Si. All right. Are we going to do something different here? Some new technique?
No.
No. Same technique. 0.0535 moles of nitrogen. Multiply that by the ratio from the equation above, which is 2 to 1. So we're going to put 1 mole of silicon nitride in the top. Over 2 moles of N2. That's the relationship from the balanced equation. That's why balancing is of the utmost importance. Everything hinges on having that equation balanced properly. All right. So that's going to give us, so this gave us 0.237 moles of product. Let's see how much this gives us. This is going to be 0.0535 divided by 2. It's 0.0268 moles of Si3N4. All right. Which one is less? 0.0268 or 0.0237?
0.0237.
Right. So what that tells me is that based on the amount of silicon that's present, I'm going to get 0.0237 moles of product. And then the nitrogen is going to give me 0.0268 moles of product. So the silicon is what we call limiting. Right? Silicon gives us the least amount of, that's the other definition. It's either the reactant that gets used up first, or it's the reactant that gives us the least amount of product. Right? So when we have 2 grams of silicon, 1.5 grams of N2 going to silicon nitride, silicon is going to be the limiting reagent. Right, so silicon is my limiting reagent because that gives me the least amount of product. Now, let me ask this question. With these numbers, how much N2 is going to be left over if the silicon and the N2 react together to give me that product? How much? So, because if silicon is limiting, the other concept here is that nitrogen is what we call excess.
So then do you just subtract those numbers?
Subtract the numbers out. It'll be something like 0.0031 moles left over of nitrogen, right? Because if what we're assuming is that they're reacting 0.237 moles of silicon is reacting with 0.237 moles of nitrogen. So what's left is 0.031 or 0.0031, something like that. Right, so nitrogen is excess and silicon is limiting. And if you want to find out how much excess is left, you would just subtract the limiting from the excess to see what's left over of the excess. All right, questions about that? So limiting reactant is, again, the reagent that gets used up first or the reagent that produces the least amount of product. We're going to put that in here. Right, excess means that there'll be some of that reactant left over after the reaction is completed. All right. All right, any question? So we'll have to, we're gonna do percent yield, which is figuring out how the theoretical by using the limiting reactant. So we're gonna do that Wednesday, and then we're gonna do an example of a titration. And after that, we're gonna move on to the next section. All right, questions, any questions? All right, I'm gonna clean these notes up